Okay, morning everyone. Sorry, the light's a bit flat today. We've got snow outside, so it's going to be a little bit blue. Right, okay. This is probably the most useful section on the first half of magnetic fields. It's the bit about the fact that we can use magnetic forces in really quite a wide range of things, but very much about the idea of particle creation. Okay, so we're leading us into particle physics, which is a big section in terms of say forces and so on. So when we get there, this is a little picture of pair creation. Won't explain it now. However, I've made a pair of particles, and the idea is that they move in a way that makes them identifiable. So this is my artistic impression of a proton, an electron and a positron being created. Okay, so how do we tell which one's which? How do we know what's going on? It's all down to this magnetic forces. Okay, so section 3. Right, okay, now the maths of this is fairly straightforward, and it still sticks with Fleming's left-hand rule. Okay, so what we'll do is just that simple idea that we go back on what we've had already, which is that we know for charges moving through a wire that we end up with the force being the old Bill. Okay, B-I-L. I say a capital L. So we've got the force acting on the current flowing through the length of conductor that's in the magnetic field. Okay, but of course there's no such thing really as current. It is actually individual particles with a net flow along the wire. Again, back to last year's work on navy. The current is the navy. So the current gives us that number of particles that are flowing through a cross-sectional area along a certain length of wire at an average drift velocity, etc, etc. If we simplify it to what we had before, I we know is Q over T, or shall we say dQ by dt. Okay, so rate of flow of individual charges, or charge itself. Now if we substitute that in, then what we end up with is BQ L over T, and basically L over T is the length it's travelled in the time it's taken to get there. So it's basically giving us that velocity. So we end up, very simple substitution, into a far more useful version, tends to have a capital Q, but far more useful version of the data sheet. And this is talking about individual charges. Okay, now this is of course in coulombs, whereas electrons, there's a lot of them, etc. But we can scale it down. This will work for whatever value of charge that we've got. Now, we still need that. We still need to use that left-hand rule. Okay, but the difference is that instead of the whole wire being pushed in the direction of the thumb, so your current flowing through your conductor there, and your magnetic field across it pushes the wire up, well, you've got individual charges that are moving along the wire being pushed up, and as they do that, they're actually going to be pushed up in a curve. Okay, so as they go up, the force will change. However, it will still be 90 degrees. And so if your force is always at 90 degrees to your motion, you get a particular type of curve, which of course is a circle. Okay, so any charge going through, any single charge, charged particle, charged ion, subatomic particles, protons, electrons, etc., but any charged particle, so not neutrons, flowing into a magnetic field, which in this direction here is down into the page, you'll get a force at right angles, and it will stay at right angles, so we'll end up with a perfect circle with your center at some point. If it's got a bigger charge, it's going to get a bigger force. If it's moving faster, it produces a force. If you have no velocity, there's no force. Okay, so if you just had an individual proton wobbling ever so slightly on the spot, it's not going to be turning in any direction. It's not really going to be affected much by the magnetic field, noticeably by the magnetic field. Okay, so yeah, if this was your setup here, your current would come in along the wire and actually just get pushed up into a vertical circle. Okay, and as long as it stays in the magnetic field, it keeps going in a circle. If it goes through and comes out the other side, or if it goes into a fairly large one and reaches the top and then comes back out, then you've changed its direction. At no point have you changed its speed. Okay, because the force is at 90 degrees. So this does not change the speed at which it moves, it changes direction. Very important idea. Okay, so let's just move it on a bit. Okay, so this kind of thing about the circle, what we can do is very simply find out details about it, and that leads us very rapidly into useful stuff. So how big is the circle? Well, it's moving in a circle, so therefore the thing that is creating the force, and I'm going to go down to little q here because we tend to be talking more generally about individual little charges. So BQV is going to equal the force that makes it go in a circle, and this one is the more useful format rather than the m omega squared r. Okay, so we can actually talk about velocities of particles because we did work on electron guns working out the speed of particles, so we know the speed, we can work it all backwards. So far most useful way of doing it. It does mean that we end up with the b's cancelled out, etc., and it comes up with a nice convenient form. Notice that's an r, not a v. Okay, so brilliantly, momentum of the particle gives us a nice clean little equation, okay, depending on the magnetic field, the radius of the circle, etc. Now fairly obviously, because we were setting off for radius, where we can get radius, and it is just simply rearranged version of what we had there. Okay, so that's kind of useful. If you're designing stuff to work on this principle, then this is a really useful equation, but probably not going to use it as much as some of the other things like finding its velocity or finding its mass or whatever it may be. Now we can start to do more useful things as well, say making them into machines by designing it to go round and change things, but to do that we need to use the idea of time to do it. So here actually I'm going to swap over to angular velocity because it just makes the math a little bit easier to do, but we can, we can do it in various ways. So maybe work from this one where we had the equation from centripetal force area. Yeah, you could use that, or you could go straight in with m omega squared r. Doesn't really matter too much. Okay, centripetal force, yes, mvv over r. If we substitute for one of those, that ends up with m omega rv divided by r, and we end up with the r's crossing out. So we end up with a kind of a useful form, a slightly different order of letters, sorry, but mv omega. So we can use that. You could do it from other principles, they're all equivalent, so it doesn't matter where you start really. But what we can end up with is the idea that that centripetal equation there means that we can bring in, like we have before, time. Okay, we could bring in frequency. Well, let's do frequency because most people are happy with that. So omega 2 pi f, or of course you could have it as mv 2 pi over capital T for time period. So they're kind of useful midpoints to get to, but basically it just means that we can work through to get the speed and the time it takes to do something, and there is something very useful at the end of this. So if we take what we've got up here, okay, we've got BQV is our force, okay, and bring that in. We've got that the force is equal to what we've just come over here, so mv2 pi. I'm going to go for the time one because it just is often easier to measure time than think about frequency. That clears out a little bit, so we can get rid of the v's. Not a lot of clearing up. I'm going to neaten up as well. Most people would be more happy with that way around. So 2 pi m over t, okay, and which means that we can rearrange that to get the time it takes to do one full orbit, which is 2 pi m. I'm going to put that over at the side in a second for a reason, b and q. Okay, now that inverse, unfortunately, q over m is the specific charge, what's known as specific charge, so charge per kilogram, and that is what was used by doing work like this to find out the value for this unknown particle that was discovered by J.J. Thomson. So this is the work that actually led us into the ideas of how big is this circle, therefore what is this unknown particle, which we still do. But originally it was to find the charge to mass ratio of an electron, to be discovered electron. Okay, so that's a really nice kind of little way of doing things, is you can find out the time by looking at the radius, etc. And the crucial bit is, the reason I've just plodded through that is you don't have this idea of velocity anywhere. So it doesn't matter how fast it's travelling, the time it takes to go round in the circle is the same. It just depends on, obviously, the magnetic field, how strongly it curves, but the charge to mass ratio. So it doesn't depend on velocity. It also doesn't depend on another crucial factor. Okay, so if you look back up there as well, you don't have to worry about radius. Okay, so underline that and put in brackets all the radius. But either way, we're getting in charge to mass ratio here and there, so we're getting it in different ways. But if we did it up at this point, we'd need to know the speed. And to do the speed, well, it's not too hard, we can work that out later. So that's charges going in a circle, and that really is the mathematics of it. It's not hard. Nearly everything keeps coming back to this area. Make your forces equal, just like we did with everything going in a circle. Now, why is that useful? It has so many uses, and that's the important bit. So I'm going to link it in here with our little calculation. I'll just slide that into the top of the picture there. One of our big accelerators, our big things that we do is we use cyclotrons to accelerate particles. So most particle accelerators around the world are in hospitals. If you want proton therapy, or if you want to use positron emission, PET scans, anything that uses subatomic physics, subatomic particles, is often, most things I say, is often in hospitals used as some sort of therapy or diagnosis system, of which we'll look at imaging right at the end of the year. So the first thing they do is they need a particle accelerator to make these particles have enough energy. And the simplest one is using that idea of what we've mentioned before, a linear accelerator. We have exactly the same setup here, but instead of a whole load of tubes which then accelerate our electron or positron or whatever it may be, let's just do that, there we go, from etc. That has a limitation because the maximum speed, the maximum energy depends on how long a room you've got. So if you could curl it round in a circle, then we can confine that in a little space. Okay, and the crucial bit with this is that we're doing the same thing. All we're doing is connecting those with an in phase, or an anti-phase to be exact, connection between each electrode. So we accelerate, say, an electron with a negative charge. We'll accelerate it if that is positive and that is negative. By the time it's going through this gap, it needs to have swapped the other way around. Then it goes through the next gap, and again our bunches of electrons to be exact, will be kind of two gaps apart, so they're always accelerating across the gap. If we take some sort of radioactive source that gives us the right or emits the right kind of particles, so I'll put it in here, it's a radioisotope. Okay, some sort of unstable isotope that gives out radiation. There we go, that'll do for the moment. Chapter 21, we'll go into a little bit more detail. So here we have some sort of radioactive source, for example beta particles shoot out, they're electrons. If we can create a magnetic field, then as they shoot out they'll go round in a circle. If we connect our voltage across there, then if the charge in front on this plate, it's actually a hollow capital D shape, as I say in my notes in the lesson where we'll do that, it'll accelerate across that gap. Okay, so this is your acceleration zone. Notice it's due to the electric field. Okay, it's a difference in voltage. So electric field accelerates, then it drifts round at the same speed from our calculations above, and then it will accelerate again, and then drifts round at a constant speed and accelerates again, and drifts round, accelerates again. So our magnetic field is doing the turning, okay, everywhere that it's basically just going at a nice constant speed. There's a slight bit of turn here, but don't worry too much because the gap's very small. The acceleration is due to jumping the gap. And if we go back up to our maths here, what happens is as that mass in that field with that charge goes faster and faster, the radius goes bigger and bigger. So if you double the velocity, you need double the radius. So it spirals outwards as it gains speed, and basically the maximum speed of the particles from this machine is determined by the radius. So if you have a bigger radius, they'll come out faster. Okay, so it's a genius little system that makes it all work. And it says there it's all about that time that it leaves. So if we just take what we had up here, again the velocity is just simply that rearranged, BQR divided by mass. Okay, so it's all come from that same basic first equation. Nearly all of them do. There's our specific charge, so again we could use that, etc, etc. So if we know the values of this, charge to mass ratio of an electron is about 2,000 times bigger, sorry, 1,860 times bigger than the charge to mass ratio of a proton, etc, etc. So we can do all the maths with it and work those out. We use the same in chemistry an awful lot of the time. So we have these mass spectrometers, and their principle is very simple, that instead of a full cycle like this, you have a magnetic field causing a radius. So here's our ionized sample, whatever it is. I had a very interesting conversation with someone who ionized to test the purity of honey once. So tiny food substance, heated enough so the ions, so they ionize, they lose some electrons, and then they fire that ionized sample through here using accelerator stage at somewhere around this part. They'll then go into here, and for this again we'll use the same equation. They will all have the same mass, sorry, the same velocity roughly. They're all roughly the same mass. They're going to have a certain strength of flux density there, so I should label that on that one as well. So that's our B. Okay, again going into the page or coming out of the page doesn't matter too much, likewise here. And so we end up with our force, so our charges moving through. Okay, as they move through the magnetic field, depending on the direction of the field, this one would have to be upwards out of the page, because then your force gets pushed in that way. Okay, but the bigger masses will produce a bigger radius for the same velocity. So our more massive particles, the ones that are far too massive, will just hit the side of the container that it's in. Okay, so evacuated containers, there's nothing to slow them down. They'll shoot in, and the big ones will crash off the side here. The really small ones will have a really small radius, so really small masses, small radius, and it will hit this side. Obviously you tune this so you try and get all your samples hitting your detector at the end. But very simply, when you're looking at mass spectrometers, you're looking very much like, sorry for another beep, more particles hitting here. So this is basically is the amplitude of our signal, the brightness of our light, if you think of little flashes hitting it, just like the spectrometer reading of colours, except it's not about angle, it's about mass, or rather, I suppose you could say different angles require different masses. So you've got a scale of mass along here, biggest mass, smallest mass, and how many hit the screen gives us that. So we can get a breakdown of the chemical ionic signature of your sample up here, because you've got that idea of how much you've ionized them, and you know, obviously their mass, so you can tell a lot about it. It's a bit more complicated than that. You have different masses, different charges, etc., etc., but you can break it down. Okay, so crucial thing is, again, it's about that radius, and it gives us that specific charge, so the charge to mass ratio. Again, exactly the same, but with R rather than M as the subject to the equation. Now, there is another use, so I'll just another example. Okay, if we just, what I'll do is just kind of pick out the main point. I'll put that on. So again, same equation before we move on. This one is that the radius is proportional to the mass. Okay, so that gives us that, basically sums up that whole process. Whereas this one up here, it's all about the velocity being proportional to the radius. Okay, so V proportional to R here, but they all come from the same equation. This one here, we got a similar thing. Now we do need a stage usually to try and slim some of these out. You want to kind of unify the particles coming in, you want a similarity. So we can use what's known as velocity selectors, and we will do this in all kinds of accelerators, okay, for whatever the purpose. And the simple thing, and this leads us into actually the demonstration I want to do, if we can get back to college I'll record it or ideally show it to you, is that we can use the charge to mass ratio to find out radius of circle and so on, and we can make that fight against an electric field. Okay, so if we have forces acting opposite each other, so here I have a magnetic field, for example, forcing these particles to go up due to their charge. If we have an electric field at 90 degrees, so it's all about 90 degrees, so they're being forced down, then depending on their properties, ones that have too much mass, or for example have too much charge, will go up or down. If there's too little of those, it will do the opposite. And what you end up with is that only the right speed with the right properties coming through will go through in a straight line. So it's a way of cutting out particles that are too fast or too slow, basically, where they have the same mass tends to be picked up here before you get to here. But if you've got the right properties, they'll go in a straight line. So you can make sure that all the particles that are being accelerated into your mass spectrometer, or maybe, you know, particle accelerator of different varieties, there are more than just cyclotrons, are all of the same variety, shall we say. Okay, so how does it work? Well, we're just having the force of an electric field equals the force due to a magnetic field. Okay, so at that point you've got balanced forces. So for linear motion, okay, and again, it's just the mathematics. We know how that works. It is in the diagram there, to be honest, but the force on a charged particle due to an electric field is Q times E. Some people said EE. It doesn't need to be an electron, it could be whatever, but there we go. We know that we have BQV from, again, the top, and so yeah, the charge is irrelevant to it, so it doesn't matter what kind of ions you've got. It's actually down to the fact of the strength of the electric field versus the magnetic field for certain velocities. So the velocities that come through, V linear, so the ones that actually pass out, will just be simply that ratio of the two field strengths, electric field strength to flux density. Okay. Next, back to my first picture. If we have particles being created due to various things, the charge that they've got and the momentum, and so on and so forth, and how fast they were moving in the first place, you know, a whole host of reasons. Now basically the particles will normally shoot off, and they'll shoot off in that kind of direction, repelling apart but going pretty quickly usually, so whizzing off into the distance. What you want to do is be able to find out what the properties are. We know that one will be plus and one will be minus due to the mathematics of it that we'll get into on another day when we do particle stuff in the next chapter. But if we can put a great big strong magnetic field around it, then they will again curl off. But left hand, let's go with this, it's a bit dodgy, but left hand and right hand curves come from the fact that you've got different charge. So positive charges will go in one direction, negative charges in the other, etc. Okay, now this is where I'm going to pick out the most important thing from the equation to do with that. Okay, so in this version, I'm going to just pick right back to the first bit. Where we've got this current, this is our idea of conventional current. So this, very importantly, is positive charge. Okay, hence my plus Q here. So your finger needs to go in the direction of positive charge. If it's negative, then your force will be in the opposite direction. That's all you need to do. You do not need to go any deeper. So here I have, say, a positive charge due to the magnetic field going that way, negative in the other. They will curl round in perfect circles. Unfortunately, to leave a trace, they need to bounce off the detectors on the way. So you basically got a bit of a Geiger counter or a cloud chamber when we get to there. So they're bouncing into stuff, which means they slow down. And as they slow down, the radius gets smaller. So they spiral inwards. Smaller and smaller until they disappear. Okay, so V again is proportional to R, so as they lose momentum, in fact, to be honest, you can have M, let's put M V there, so the momentum, so as momentum is lost, you get smaller circles, smaller radius. Okay, so you get smaller radii, plural. Okay, if you have a large momentum, you can have a large radius. So the size of those circles literally will tell you the charge to mass ratio. They will literally tell you how massive the particles are. Okay, a bit later now, a bit brighter. Right, all of those experiments that we've just been looking at just give you a way of actually finding out something that's really difficult to do. Let me just find a sheet. So if we look at those, these all have a purpose. These are to give you different speeds of particles, because it's a particle accelerator. This is to separate them out by using their mass. So you're looking at that idea of mass as they go around the circle to give you a certain size of circle. That certain size of circle is also useful to choose the right velocity. So we're trying to filter out those that are too fast, too slow, because of different properties at the beginning. And we can also use it to detect, again, effectively this is a mass spectrometer, it's just in a different way. It doesn't give us a picture, we actually have to detect it in a different way. But none of them get around the fact that we actually need to be able to measure the magnetic flux density, and it's really difficult to do, and this is where this comes in. So what we use is a semiconductor, so in this case, as it says, germanium, and I'm going to do a little bit of video to use this because we don't usually get the chance. But what happens is if we let current flow through the material, well, because you've got these free charge flow, charge majority carriers, or majority charge carriers if you prefer, as they flow around from top to bottom, they will be restricted a little bit. They'll be semi-resisted, but there's enough that's flowing through. If we can slow them down enough, okay, so this doesn't really work with the conductor, but it does with the semiconductor. If we slow them down enough and we stick a magnetic field on, so if we put a magnet on top of that, it just about fits in one way, there we go, on that way. If we put it on top, then what happens is the field that flows down into it as your current flows in gives us a third direction. Okay, so again, it's Fleming's left-hand rule, and our conventional current, our positive charges that flow in, will be pushed by the magnetic field sideways. And so what we end up with is we can get a measurable voltage, and the voltage will just depend on some really basic ideas. So by measuring that voltage, we can work out the strength of the magnetic field. And if I take one of the magnets away, then I'll have a different flux density, and so I'll have a different voltage. Okay, and there's a little bit of adjustments and stuff like that, but that's basically the idea. So, ouch. A Hall probe is a really good way of measuring the magnetic field strength, which we can't usually do in other ways. Okay? Now, first things first, when you get this, I think I've corrected it on yours, but using the hand rule, this is wrong. Okay, so your your current flows in from this direction. So again, conventional current. So this is your plus I, okay, coming through. It's coming through that way. We want it to actually push. In this diagram, it gets pushed onto that side. So if we do that, your thumb is downwards. So actually, the flux density is in that direction. So just make sure your arrows are down. Verify it with your left-hand rule. Don't know who put the picture in. It's a lovely picture, but there we go. If you want to, you could do negative current, and if negative current will get pushed outside, it doesn't really matter. It ends up with the same effect. But yeah, let's just go with positive charge. So what happens is the charge gets pushed across, and it will build up and build up and build up until you get basically a capacitor, an electric field building up across here. So our charge will start to repel any more electrons. So you'll get to a point at which the charge from the magnetic field and the charge from the electric field cancel out. So at equilibrium, again, it's always about at equilibrium. Fe equals F. I usually use B, but let's just put mag just to make it clear. Okay. Now the thing that it works on, it all depends on the size of the material as well, and the number of charge carriers that's in it and stuff like that. So we need a little bit more detail. But the key point from this is this charge is measurable. This is your Hall voltage, as it's called, the Hall effect voltage. Okay, so that's your measurable thing. You're trying to measure across that place. So if we just take those, well, we know that our electric field strength is of course to do with our voltage and stuff like that, but we'll come back to that. So I'm just going to put in there, so BeV I'm going to use. Again, little v, it's velocity, so not BeV, which we're used to electron volts. It's not to do with that. It's E little v. E being electrons, because we're assuming that it is a standard current of moving electrons, really. Okay? So, in this case, V is, as I mentioned before, drift velocity. Okay, so it's actually quite slow, and we didn't do this because lockdown has given me the chance to video it, so I have videoed, and if you look in module 4, If you look in the videos there, I've got a video of drift velocity. So I charge positive and negative charged ions in a damp carrier and they move apart. Okay, so that's worth looking at. So from that, it comes from that's a terrible I equals NAVE. That's the equations on your data book, where that's your number of charged carriers per volume. Okay, so that's number per volume. That's your drift velocity, that's your charged electron, and that's the cross-sectional area. So I actually need a different dimension. So I've got my depth, and I'm going to have my width as well. So I'm going to just put that into there. Okay, so just make sure it doesn't look like an omega. I'm going to pause that because I need to carry on with lesson. Okay, part 3. So halfway through the proof, we have two forces that are balanced: a magnetic field force due to the magnetic field and the force due to the electric field. So these two are fighting each other. One's at right angles, admittedly, but yeah, they are directly facing each other, so they are fighting each other. So our force due to our magnetic field on the moving charges, moving electrons, is BeV, and we said that we have our current made up from the drift velocity of those charges through a certain area, etc. So what I'll do is I'll just conveniently rearrange that. So VE, they're both in there, so might as well keep them together, is I over NA. So we can stick this into our equation, but let's clear things up and just make it really clear. So my magnetic force is going to be B multiplied by EV or VE. So I've got BI over NA. Okay, so cross-sectional area as seen by the current. Okay, number of charge per unit volume of our semiconductor. B is our magnetic flux density. So if we go to simplify that, we're going to, you'll see in a second, we'll make that equal to something else because that will help. But if we think about the electric force, okay, and again I'll make it a bit clearer. So we know that it is EE, okay, for a nice parallel sided field, which it is, field lines running across. But realistically, we're after measurable voltage, so that's going to be EV over the distance between the two sets of charges. So that's W. Okay, so V over D. It's just that D in this case we have used as width. So what we've got is basically those will equal each other. Now, I can simplify this top one because I've got W down here. W is part of the area seen by the current. So this is more easily shown as N depth multiplied by width. Okay, so our cross-sectional area at the end. So what we've got is going to be those two are equal, so we end up with E V over W equals B I N D W. So the W's are irrelevant, so it does not matter how strong your electric field is, it will still work on a narrow piece. But what we basically end up with is a version that can recreate and convert around. So just going to add in to pick up with our symbol up here. I'm going to change that to H because that's what I'm after, my Hall voltage. So to get that, I'm simply going to have our final equation, which is the voltage that is measurable with our voltmeter depends on B, depends on I, because if they're flowing faster they're going to get further, you know, things like that. And then ND, let's stick it that way, NDE. Okay, so that is really about the only way we can really measure B, flux density. Okay, we need to know the current, and the rest is just dimensions and known values. So really simple way of finding it once it's reached at equilibrium. So once it's settled down a bit, so you need to wait a little bit for the voltage to stop changing. Okay, but they do like this. This has appeared a couple of times, and they do mention the Hall probe, so in the specifications, so do make sure you're happy with that. Okay, So today has really been, this chart has really been about the basics, okay, the basics of the movement and its uses. So there's nothing nothing really clever about it. I've lost my page, there we go. It's mainly down to just the use of that equation which is given to you, or E if you prefer for electrons or fundamental charge. Just beware, you might have an ion which has 2 charge, so charge plus 2 for example, so it's 2 lots of E. But yeah, that other bit is everything really stems around from centripetal force, because it's going in a circle caused by that force. So you make the 2 forces equal, and if you need to bring in time, then just bring in omega somehow. So either as, maybe go for m omega squared r instead here, and that would do the same trick. So as long as you get omega in, omega being 2 pi over t, or 2 pi times f, 2 pi over t usually works better, that can work everything out. So it's just balancing forces, that force and the fact that it's moving in a circle, and I should point for a positive charge, a negative of the same variety moving at the same velocity would move in the same curve but just in the opposite direction. Okay, so just swap the direction of the arrows, so just make sure it's always plus. And as I say, all of those machines that we've used for different reasons, the cyclotron, the mass spec, velocity selectors, which combined give you particle detectors that we're going to mention quite frequently, and more importantly this for the spec, with the arrow down because of the left hand rule. Keep sticking with those. Okay, practice the questions for section 3, section 2 and section 3. They are the ones that come up all the time. That takes us to the end of the first half of the chapter, which is about forces. The second half is creating electricity, so we need to get into kind of more descriptive stuff. So that's a very definite end for that chapter. Okay, so rule it off there. Great, thanks very much.